Hey, AP Calculus BC. Today we're going to be learning about lesson 3.5 titled Particle Motion Revisited. In this lesson, we're going to be in College Board's Unit 8 here in this second lesson called Connecting Position, Velocity, and Acceleration of Functions Using Integrals. If we take a closer look, the essential knowledge for this lesson is that for a particle in rectilinear motion over an interval of time, the definite integral of velocity represents the particle's displacement over the interval of time, and the definite integral of speed represents the particle's total distance traveled over the interval of time. And this is a topic that we've discussed before, but there's a difference between displacement and total distance traveled, right? Think about if a car is kind of going along a straight line and it starts maybe here. I know my video might be pretty small, but I bet you can see this. So if a car starts here, it travels this way and then it goes in reverse and stops here, right? The total distance traveled would be from here to here and then from here to here. So it's going to be a lot further than the displacement, which just means what's the difference between where we ended and where we started. Now we care about this because, for example, in the case of a car, the amount of gas or fuel that's used up, that doesn't care about displacement, right? Like if we travel this way and then travel back, the amount of fuel doesn't kind of like replenish or come back because we went in reverse. That doesn't matter. So the total distance traveled is what would be taken into account for fuel usage. But displacement might be kind of like the bigger picture, like, well, how far did we get in the end? You know, and depending on the application, we'll care more about that, for instance. So this lesson is going to be, some particle motion types of free response questions that you've seen before, and some that will potentially involve average function value that we learned in the last lesson. So I'm going to open up the notes and we'll get started. All right, so here we have the notes. We're looking at lesson 3.5 again, particle motion revisited. Particle motion problems occur frequently in AP Calculus, and many involve a fundamental theorem of calculus, displacement versus total distance traveled, and technology. This section provides a brief summary of results and several problems involving these concepts. So let's take a look. We're just going to move right into the first example, and this example is 4 parts. Particle moves along a horizontal line. For 0 is less than or equal to t is less than or equal to 8, the velocity of the particle is given by this v of t function, and the position is given by s of t. It is known that s of 0 equals -3, but the actual function for s of t, the equation, is not given. All right, part A. Find all values of t in the interval from 4 to 7 for which the speed of the particle is 5. So the first thing that we need to know in order to answer this question is that speed is the absolute value of velocity. Speed doesn't matter if you're moving forwards or backwards. It's always positive. So if the speed is 5, then velocity, there we go. The velocity can be +5 or -5. So what we're going to do is we're going to use technology or our graphing calculator to help us with this. So I'm going to graph v of t and the horizontal lines y equals 5 and y equals -5 to look for the points of intersection. So if I pull out my graphing calculator here, and I go to y equals, to save time, I already typed this v of t function in as y1, and in y2 I typed 5, and in y3 I typed -5. And when I go to graph, you can see that this blue curve, which may not appear blue for you, but it's the curve, that's the v of t function, and then we've got these 2 horizontal lines. And our job is to figure out between 4 and 7 on the x-axis where does that curve intersect these lines? So we've got 1, 2, 3, 4. And I can't really tell based off of this. It looks like that intersection point is a little bit to the left of 4. So 5, 6, 7. I'm thinking we have 2 intersection points, one here and one here. But we can check. If we press second trace, again, that's second trace, and you go to intersect, you can choose 2 curves in the approximate location of the intersection point to figure out what the value is. So I'm going to go up here on the curve to right around here. And then for the second curve, if I click the up and the down arrows, it lets me pick which curve I want to use, and I want to use the red one. So I'm going to stay here and click enter and wait for it. It tells me the intersection has an X value of 3.65, and that's smaller than 4. So we're going to move on. I'm going to go back to second trace, oops, and go to intersection again. I'm going to move to this one now. So on the blue curve, I'm clicking right about here. And on the red curve, or red line, I'm going to click right about there. And this one is 5.621. And that, indeed, is between 4 and 7. So that's definitely one of the t values where the speed is 5. And I think there's going to be one more down here. So let's check. I'm going to go down here. Now it's telling me it's assuming I want to use that top line, but I don't. So I'm going to click the up and down arrows until I get to the other line. Hit enter. And this one's at 6.520. And that next intersection point is definitely too far away. So these are the 2 points in time where our speed is 5. Now, for one of them, the velocity is positive 5, and the other one, the velocity is negative 5. But the speed is the absolute value. So the speed is just 5 for both. So that's the answer to letter A. In letter B, write an expression involving an integral that gives the position at s of t. Use this expression to find the position of the particle at time t equals 3. All right, so here's what we're going to do. We're going to start our s of t with what we know, which is that we know s of 0 is negative 3. So if we start at 0, we should be able to add the integral of our v function from 0 to whatever this t is over here. And because we've already used t, I'm going to change the variable of v to x. So you can see that for any t that we plug in, we have this v function. We're going to go from 0 to that t value and add that area to the initial condition at s of 0. And that'll give us our position function. And that's pretty much the best we can do for an equation here. We're not actually going to be able to integrate by hand because I don't really want to deal with that. And the question doesn't ask us to. So it just says write an expression involving an integral. But we can get a little bit better. We can plug in negative 3 for the s of 0. So I'm going to plug that in. And then the question says to use this expression to find the position of the particle at time t equals 3. So now I'm going to actually find s of 3. Okay, and we can use technology to help us with this. So if we go back over here to the calculator, I can plug this whole thing in here, and it'll give me the answer, right? So I can start with negative 3 plus, and I'm going to have my integral here with my bound. So I'm going to plug in 0 and 3. And for v of x, I'm going to plug this whole function in again. So we have, and I'm using x instead of t. Okay, so far so good. Plus 2x sine of x squared over 12. Okay. dx. And we get negative 6.263. I'm going to round to 3 decimal places, negative 6.263. There we go. So we found the position when the t is 3. Letter C. Find all times t in the interval from 0 to 8 at which the particle changes direction. So a particle changes direction when the velocity changes sign, right? So if we have a positive velocity, we're moving one direction. If we have a negative velocity, we're moving the other direction. So whenever the velocity switches sign, the particle is changing direction. I'm going to write that out first. So the particle changes direction when v of t changes sign. Okay, so I'm really looking for on the graph when v of t equals 0, because if you look again at our graph, I'll delete those 2 horizontal lines here and just kind of look at the graph again. We're looking from 0 to 8, 1, 2, 3, 4, 5, 6, 7, 8. There's 2 points where we're changing from negative to positive or positive to negative with the velocity function. So I can go to second trace, find the 0. You probably have a lot of experience doing this, so I'm not going to talk through the steps. This one's at 2.341. And that one changes from negative to positive. The velocity function does around that point. And I'm going to go find the other 0. A little bit to the left, a little bit to the right. And we get 6.127. That's changing from positive to negative. Okay. That brings us to letter D. Is the speed of the particle increasing or decreasing at time t equals 7? Give a reason for your answer. So this is really asking, are we speeding up or are we slowing down? And to figure this out, we need to find the velocity and the acceleration at t equals 7. So to do that, first of all, we can just look at the table to get the value for 7. And because this is the velocity function that we graphed. So we get negative 10.912. For the acceleration, remember that's the derivative. So what we can do is we can go back to the home screen and we can type this in as a derivative. I'm going to pause and type that in and then show you what it looks like. All right, I just wanted to make sure that I had that right. So this is what the calculator shows when you type in the derivative of the velocity function. First, you can go to math and click on number 8 to get a derivative. And then you don't actually have to type the whole thing in from scratch. Since we already entered this as y1, if you click, I'll move this up a second. Ooh. If you click vars down here, this button, and then go to yvars function, you can click y1. Again, that's vars, yvars function, y1. And then in parentheses, I put an x. And then I want to evaluate when x is 7. And if I click enter, it finds the derivative at that point for me so that I don't have to do it by hand. We get negative 10.561. Okay, so we have our velocity and our acceleration. And so our conclusion can be that the velocity and the acceleration have the same sign. Therefore, remember these 3 dots in a triangle mean therefore. Therefore, the particle is speeding up. Or you could say that the speed of the particle is increasing. Okay? So that's the end of example 1. Let's keep moving. Example 2. The Space Shot is an amusement park ride that gently raises riders up a tower, then rapidly bounces them down using compressed air. The velocity of the Space Shot for 0 to 14 is modeled by a piecewise linear function shown below, where t is measured in seconds and v in feet per second. So this time we don't have an equation, we have a picture, we have a graph of the velocity still. So part A, at what times in the interval from 0 to 14, if any, does the Space Shot change direction? Give a reason for your answer. And this, similarly to an example 1, we can discover by thinking that the direction changes when the velocity changes sign. And so if we look up at our graph, this happens when t is 6, change from positive to negative, when t is 8, change from negative to positive, and when t is 10, we change from positive to negative. All right, so that is when we change direction. Letter B, at what time in the interval from 0 to 14 is the Space Shot highest? How high is the ride at that time? Interesting. Okay, so we need to think about that we want to set up a candidates test, and we've already found all of our critical points when the velocity changes sign. So we are going to test the endpoints of the interval, 0 and 14, and then 6, 8, and 10. But the question is, what are we testing? So remember, we are interested in when we're highest, and that's a position, right? The highest will be the position. So we need to define a position function here, and our position, for our purposes, is just going to be from 0 to t of v of x dx. So it's the integral of the velocity, right? That makes sense. And we're going to assume that the initial position is 0 because it's going to start on the ground. As the statement at the top said, it raises riders up and then rapidly bounces up and down. So we're starting at 0. So that's why our initial condition is 0 plus this. We don't even write that part. And so over here we have s of t. So at time 0, we're at a height of 0. At time 6, the best we can do here is actually try to calculate this using area, because we don't have an equation to plug into. So at time 6, our job is to figure out how high did we get, or what is this area in here. So the y-axis or v-axis is counting by 20s. So this little triangle right here is 1/2 times 1 times 20. So it's going to be 10. We have a rectangle here with an area of 80, and then another triangle with an area of 10. So at time 6, we have a height of 100, or a position of 100. And then our next critical point is 8. So if we take a look back up here, we're just going to start with the 100 that we just had. And then from 6 to 8, what do we got going on here? We have a triangle with a base of 2 and a height of 60. And that's below the x-axis. So it's going to be minus 1/2 times 2 times 60. And that is going to equal a total of 40, because the 1/2 and the 2 cancel out. So at 8, we were at 40. At 10, we're going to start with that 40. And then we have to add this triangle. So we have a base of 2 and a height of 40. And that's going to take us up to a height of 80. And then at 14, we're going to start with that 80. And we got to subtract this whole triangle down here. So we have a base of 4 and a height of 40. And we're going to end up with 0, which is good. We ended back on the ground so that the riders can disembark, right? So this is all of our positions, and you can see that the biggest one is right here. So the Space Shot is highest. at t equals 6. And the question says, how high is the ride at that time? The ride is 100 feet high at that time. And performing a candidate's test is a valid explanation of why that is true. Okay, so we don't need to write any more explanation. Letter C, find the total distance the space shot travels during the time interval from 0 to 14. Okay, so total distance traveled. In order to find the total distance traveled, we're interested in the absolute value of the velocity. In other words, we're taking the integral from 0 to 14 of the absolute value of velocity. And here's why. If we just did the integral from 0 to 14, we already know that we would end up with 0, right? Because we started at 0, we ended at 0. All of the positive area canceled out all of the negative area. We ended up back where we started. So if we just took the integral of the velocity, we would end up with 0. But we know that this space shot did travel, it moved. So if we think about all of these negative areas kind of being reflected up above the x-axis or the t-axis, what we would find is the actual distance traveled. And another way of thinking of this is splitting this into chunks based off of our critical numbers. Every time that the velocity equaled 0, we're going to split into a separate chunk. And so I'm going to split this, and we're going to go from 0 to 6. And from 6 to 8. And from 8 to 10. And from 10 to 14. Okay, so I'm writing a whole bunch of integrals here, but we're not going to have to do that much work in the end, believe it or not. So from 0 to 6, the question is just what changed, or what's the difference between these two numbers? So I can write that in absolute value, that we ended at 100 and we started at 0. So it's 100 minus 0. From 6 to 8, we went 40 minus 100. From 8 to 10, we have 80 minus 40. And what I'm doing right now is evaluating these integrals, but I'm leaving the absolute value bar so that we can make sure they're positive in the end. And the last one goes from 80 to 0. So I'm going to write 0 minus 80. Okay, so we end up with 100 plus 60 plus 40 plus 80. So we traveled a total distance of 280 feet. Even though we ended where we started, so the displacement is 0, the distance traveled is 280 feet. And believe me, when you get off this ride, you're not going to say, wow, I really wish that ride moved. We just stood still the whole time. No, you're going to be bouncing up and down. And this is the total amount that you actually moved. All right, letter D, write expressions for the ride's acceleration, velocity, and distance that are valid for the time interval from 10 to 12. So if we take a look up at our chart, from 10 to 12, we're talking about this interval right here. So we have a straight line segment that is valid here. So that's what we're going to be looking at. So let's start actually with the acceleration. Remember, the acceleration is the derivative of the velocity. So we're going to actually just care what's the slope of that line. It's a straight line, so the derivative is just going to be a number, and it's going to be that slope. And so in order to do that, I'm going to use the good old-fashioned slope formula. So I'm going to write out that a of t equals b prime of t, which is negative 40 minus 0 over 12 minus 10. So I took the 2 points. At 10, we had a y value of 0, and at 12, we had a y value of negative 40. Plug those in, we get negative 40 over 2, or negative 20. So that is the slope of the velocity, which is our acceleration function. Now that's not true for the whole function, but we only care between 10 and 12, so that's valid. All right, for v of t, the velocity function that's going to be true just for this interval is a line. So we already know the slope of that line is -20. I'm going to use y minus y1 equals m times x minus x1, our point slope form. We'll plug in the point 10 comma 0 and our slope of -20 and see what happens. So I'm going to fill in the rest of the formula. And I am going to distribute the -20. So we get -20x plus 200. So that's our velocity function. I could have written v of t here instead of y equals, but same thing. And then we want to know the position. And you know what? Now that I'm looking at this, the original graph and the question uses t instead of x. So I suppose I could rewrite this as v of t equals -20t plus 200. Side note, on an AP test or on a test in my class, x and t are interchangeable. If you accidentally change a variable and it doesn't conflict with something else that's already given in the problem, you won't lose points. Okay, so s of t, we want something that can work from 10 to 12. Now, we know the value of the function, the position function, at 10. So we're going to start with s of 10 and then add the integral from 10 to some t, whatever t we're using, for that position function that we just came up with. And now I'm going to use x since we're using t as a bound. Okay, but we can go one step further from this because this time we can actually evaluate this integral. So I'm going to. So we know s of 10 is 80. And this integrated becomes -10x squared plus 200x. And we're going to evaluate that from 10 to t. So we're going to get 80 plus -10t squared plus 200t minus -10 times 10 squared minus 200 times 10. And we multiply and combine like terms there, and your final answer is going to be -10t squared plus 200t minus 920. So there you go. There's your position function. That's only true from 10 to 12, but that's what the question asked. All right, so that's the end of example 2. Let's keep going. We've got 2 more examples to work through. All right, 4, 0 is less than or equal to t is less than or equal to 10. A particle moves along a horizontal line. The velocity of the particle at time t is given by v of t equals t squared minus 9t plus 14. The position is, the particle is at position s equals 15 at time t equals 0. So we have an initial condition. Letter A. 4, 0 is less than or equal to t is less than or equal to 10. When is the particle moving to the left? So particle moves left when the velocity is less than 0. So we are going to perform or create a sign chart here to figure this out. So my velocity function was given as t squared minus 9t plus 14. And I'm going to find my critical numbers here by factoring. And so what I found is that the velocity is 0 at t equals 2 and t equals 7. So I'm going to set up my sign chart. I'm going to use 2 and 7. And we actually have endpoints here, so I don't really want arrows at the end. It's going from 0 to 10, like the question said. And we are caring about v of t because we want the sign. We want to to know when the particle is moving left. And the particle moves left again when v of t is less than 0. So if you plug in the number 1, you get a negative times a negative, which is a positive. If you plug in the number 3, you would get a positive times a negative, which is a negative. And you plug in something like an 8, and we would get a positive times a positive, so that's positive. So when are we less than 0? The interval from 2 to 7. So you could write that in interval notation, or you could write 2 is less than t is less than 7. Both of those are valid ways of writing that that's when the particle is moving to the left. Letter B, find the total distance traveled by the particle from time t equals 0 to time t equals 4. Okay, so for this question, we care about the integral from 0 to 4 of the absolute value of v of t, just like we've been doing in all the other examples so far in this lesson. And we're going to split this based off of the critical number that we found in part A, where the sign switched of the velocity. So we're going to write this from 0 to 2. And from 2 to 4. All right, and so we have a velocity function that is not hard to integrate. So we're going to do this by hand. So we have the absolute value of t cubed over 3 minus 9t squared over 2 plus 14t. And we are going to evaluate that from 0 to 2. And we have to do the same thing again. From 2 to 4. Okay. That is a 14t. Just my pen stayed on the page a little extra, but we'll keep going. So what we're going to do is plug in each of these numbers, and when you plug in 2 here, I'm going to do a little bit of the simplifying for us. You're going to get 38 over 3. When you plug in 0, you're going to get 0. When you plug in 4, you're going to get 16 thirds, and when you plug in 2 again, you're going to get 38 over 3. So we're interested in adding the two absolute values together, and when you do that, you are going to get positive 20. So that's the total distance traveled by the particle. Part C, find the acceleration of the particle at time t. Is the speed of the particle increasing, decreasing, or neither at time t equals 3? So we know that acceleration is the derivative of the velocity, which in this question, because of the initial equation given, we can easily take the derivative of this, and we're going to get 2t minus 9. And so that was the first part of the question. And now it wants to know, is the speed increasing, decreasing, or neither at time t equals 3? So in order to figure that out, we have to find the acceleration and the velocity. So the acceleration is going to be 2 times 3 minus 9, which gives us negative 3. And that, last time I checked, is less than 0. The velocity is going to be, if I plug 3 into the original equation that was given, so it's going to be 3 squared minus 9 times 3 plus 14. And we get negative 4, and that's also less than 0. So if you're tracking with us here, we want to know if we're speeding up or slowing down. So if the speed is increasing, decreasing, or neither, the signs match. The signs are the same. So that means that we are increasing in speed or speeding up. So I would write the speed is increasing at t equals 3 because velocity and acceleration have the same sign. There we go. Part D, find the position of the particle at time t equals 8. All right, so we're going to use that formula again for position. where we start with the initial position that we know, which is at t of 0. So we're going to start with s of 0, and we're going to add the integral from 0 to 8 of the velocity. All right. So we know that s of 0 is 15. That was given in the last sentence of the question prompt, the initial problem stem. And we also know the velocity equation, so we can plug that in. And we've already actually integrated that, so we can plug that in here. We're going to evaluate from 0 to 8. Okay, so this time we can plug in 8 first. And we plug in 0, we're going to get 0. So if you multiply, combine all of these numbers together, you're going to get a final answer of 29 over 3. So that's the position of the particle at time t equals 8. Right? We went from velocity, we integrated, so we went up a step to the position. And that's the end of example 3. That brings us to our last example, example 4. Valerie swims along a straight line in an Olympic-sized pool. For time from 0 to 50, Valerie's velocity is given by a differentiable function v. Selected values of v, where t is measured in seconds, and v of t in meters per second are given in the table. So this time, we don't have a graph or an equation, we just have a table. So part A, use the data in the table to estimate the value of v prime of 30. So 30 as a t value is halfway between 20 and 40. The best estimate that we can do is if we think of a straight line going from this point to this point and find its slope. That'll give us an approximation of the slope at 30, and that's the best that we can do. So v prime of 30 is approximately v of 40 minus v of 20 over 40 minus 20. And that's just our good old-fashioned slope formula, right? So we'll plug in here, and we will get 1.3 minus negative 0.7 over 20. And I will end up with 0.1 meters per second squared. Because v of t was in meters per second, so v prime is going to be meters per second, or meters per second squared. Letter B, using correct units, explain the meaning of the definite integral from 0 to 50 absolute value of v of t dt in the context of the problem. So if you're tracking with us here, we've been using the absolute value of velocity a lot in these examples, and it always means the same things. It means the total distance traveled. So in this problem, what that is going to tell us is it is the total distance that Valerie swims in meters over the time interval zero less than or equal to t less than or equal to 50 seconds. That's exactly what that's telling us, right? We need to say that it's a total distance, and we need to say that the bounds from 0 to 50 are telling us the time interval where this total distance applies. Okay, so that's the two things that you would need to say. And I suppose you would also need to say the units, so in meters. So we've got distance, total distance traveled in meters, and here's the time interval. That's letter B. Let's keep going. We've got 2 more questions. Part C. Approximate the value of that same integral using a right Riemann sum with 4 sub-intervals indicated in the table. Okay, so we're going to try to write this out. And we're going to use a right Riemann sum. Okay, so if you look back at the table, what that means is we're going to go from 0 to 8, from 8 to 20, 20 to 40, and 40 to 50. And each time we're going to use a right endpoint as the height of the bar for the Riemann sum. So we're going to go from 0 to 8, so we're going to multiply 8 by 1.2. And then we're going to go from 8 to 20, so we're going to multiply 12 by 0.7 because we're evaluating the absolute value of the velocity. So we don't care about that negative. And we're going to keep going the same pattern. So I'm going to write out what that looks like on the next page. So it's going to be 8 times 1.2 plus 12 times positive 0.7 plus 20 times 1.3 plus 10 times 1. Right, so the 8, the 12, the 20, and the 10, that's the width of each interval. So we subtract the endpoints from each other. And then this is the y value, or the v of t, at the right endpoint, but the absolute value. So no negatives. So we multiply and add this, and what you're going to find is that we get 54 meters. Again, that's an approximation of the total distance traveled by the swimmer. Letter D, Jen is swimming in the lane next to Valerie. For 0 is less than or equal to t is less than or equal to 16 pi. Ah, yes, we always measure time in terms of pi. Jen's velocity is modeled by j of t equals 5 sine of t over 6, where t is measured in seconds and j of t in meters per second. Find Jen's average velocity during the interval 0 is less than or equal to t is less than or equal to 16 pi. Average velocity. And we are given the velocity. So this is a callback to last lesson when we found the average value of a function. So what we're going to be doing here is v average of 1 over 16 pi minus 0, integral from 0 to 16 pi of 5 sine of t over 6 dt. So I just plugged that function directly into this integral to find the average velocity. Now, we can do this one by hand, so we're going to. So we're going to let u equal t over 6. So du is 1 over 6 dt. And then we come back over here. We got 1 over 16 pi in front. And I'm going to change this into u now. So I'm going to change the bounds. So if I plug 0 in here, I get 0. If I plug 16 pi in here, I'm going to get 16 pi over 6, which reduces to 8 pi over 3. That's an 8 pi over 3. And then inside, we have sine of u. And I never got rid of this 5. So we have 5 sine of u. And in order to get du, it needs to be 1/6 dt. So in order to introduce a 1/6 here, I have to multiply by 6. So I really have 6 times 5 over here. And then this can become du. Okay. So next step, I'm going to move the 6 and the 5 out in front into the numerator. So we have 30 over 16, which reduces to 15 over 8 pi. 0 to 8 pi over 3 sine of u du. And the integral of sine is negative cosine, right? Remember, Santa Claus, negative Santa, negative Claus. We moved up from sine, so it kind of filtered back down to the bottom to be negative cosine. From 0 to 8 pi over 3. So we're going to plug these values in. We get 15 over 8 pi times negative cosine of 8 pi over 3 minus negative cosine of 0. And 8 pi over 3 is more than 2 pi, right? 2 pi would be 6 pi over 3. So if we kind of cycle around our unit circle, we're going to get 1, 2, 3, 4, 5, 6 pi, 7, 8. So it's really the same as a cosine of 2 pi over 3. This is negative 1/2, and there's a negative in front. So it becomes positive 1/2 minus the negative cosine of 0. Cosine of 0 is 1. So we end up with this. And so we have 1/2 plus 1. So we have 15 over 8 pi times 3 halves. And we end up with 45 over 16 pi. And if you actually kind of multiply that out to get an approximation of our answer, we get 0.895. And the question tells us that we are in meters per second. And I think that seems pretty reasonable for the average speed of a swimmer. So I think we are good. Yeah, so that is the end. Thank you so much for watching. And let me know if you have any questions. Thank you.